Okay, let's dive straight into this explainer and demystify the invisible architectures that are literally connecting our entire digital world. We use networks every single day, every hour, really, but we rarely stop to actually think about the physical and logical structures that make all this instantaneous communication possible.
Before we get into the heavy tech, I want you to think about your own home Wi-Fi, or maybe your office setup, and ask yourself how a simple email knows exactly where to go. Because when you hit send, your data doesn't just magically teleport, right? It travels across highly structured, engineered pathways. But who decides what those pathways actually look like?
Well, here's our roadmap for figuring that out. We're going to start by decoding what topologies actually are, explore the early bus and ring setups, check out the star standard, dive into mesh reliability, scale things up with the tree topology, and finally, figure out which one of these setups actually wins.
Section 1. Decoding network topologies.
So what exactly are we talking about when we throw around the word topology? Well, think of data like traffic and cables like roads. A topology is basically the literal city map that dictates how information gets from point A to point B. Whether we're talking about computers, printers, servers, or routers, network topology defines their physical placement and the logical rules for how they talk to one another across that setup.
Section 2. The early setups, bus and ring.
First up is the bus topology. Now picture data traveling along a single backbone cable, kind of like cars on a one-lane highway. Every single device connects to this one main communication cable. When a computer sends data, that data travels all the way down the line. Every single device on the network actually receives the signal. But here's the clever part. Only the device it's specifically addressed to actually processes it. Everyone else just ignores it.
Now this setup has some really clear pros and cons. It is incredibly cheap and super easy to set up for small or temporary networks because it uses barely any cabling. But there's a massive catch. If that one central backbone snaps or fails, the whole system goes completely dark. Plus, as you add more devices, performance absolutely drops, and troubleshooting exactly where the line broke can be a total nightmare. Because of this, it's mostly relegated to early, older computer networks.
So, engineers tried another shape, the ring topology. Here, devices connect in a literal circular path. Data moves methodically from one device to the next around the ring, usually just in one direction. It essentially travels along the loop, getting passed along until it reaches its intended destination. This provides equal access for all devices in a very organized, predictable data flow with way fewer data collisions.
But despite this highly organized layout, if a single computer shuts down or a single cable snaps, the circle breaks and all communication just halts. Because the data relies on each device to pass it along, a single broken link stops the entire chain. Adding or removing devices is also pretty tricky because it interrupts the flow. Today, you're mostly going to see this specific topology used in specialized industrial communication systems or fiber ring networks rather than your local office.
Section 3. The standard star topology. All right, let's move to the undisputed champion of modern everyday networking, the hero of modern Ethernet LANs, offices, schools, and our homes, the star topology. Instead of chaining devices together like we just saw, every single device connects individually to a central point, usually a switch or a hub. When one PC wants to talk to another, it doesn't shout down a shared backbone, and it doesn't pass it through a neighbor's computer. It sends the data directly to the switch. The switch reads it and securely routes it only to the intended PC, keeping the rest of the network perfectly safe and completely unbothered. This design makes management incredibly simple. It's super easy to install, and if you want to add a new device, you just plug one new cable into the switch. And most importantly, if one cable fails, only that specific device goes offline. The rest of the office keeps working perfectly. But here's the downside. It requires a lot more cabling. And if the central switch itself fails, your entire network immediately stops. That switch is the ultimate single point of failure here.
Section 4. High reliability, mesh topology.
Now, we are upping the stakes to environments where failure is simply not an option. We're talking military applications, critical banking networks, data centers, and the internet backbone itself. For them, reliability is the absolute ultimate priority. They literally cannot afford for a central switch to fail and bring everything offline. Enter the mesh topology. In this architecture, each device connects to multiple other devices. In a full mesh, every single device is connected to every other device on the network. Imagine a sprawling city grid with endless detours. If one road is blocked, the data simply finds another way to its destination. It dynamically routes around the problem.
This topology offers supreme security and fault tolerance. There is literally no single point of failure anywhere, which is incredible. But the trade-off? It requires a massive amount of ports and cables, making it highly complex and wildly expensive to set up and maintain. That's exactly why you don't use a full mesh for a small real estate office. You save it for the systems that keep the modern world running.
Section 5. Scaling up. Tree topology. So how do we build this out when organizations need massive scale, like a major university or a sprawling enterprise network? The tree topology is actually a brilliant hybrid. By combining the central control of a star with the linear backbone of a bus, networks can expand outward hierarchically, almost like the branches of a giant tree. You have a main backbone cable that connects to multiple main switches, and then each of those switches acts like the center of its own little star network, connecting to several individual devices.
This structure is ideal for large organizations because it allows for easy, structured expansion. You just add a new branch to the tree while maintaining centralized control. But it is definitely more complex than a simple star topology. And while a single device failing won't hurt much, you have to remember that if the main trunk, that primary backbone, fails, entire branches of devices will instantly lose their connection.
Section 6. Which topology wins?
The truth is, there's no single winner. It entirely depends on what you actually need. Our journey kind of proves that cost directly scales with reliability. You've got the bus topology, super low cost but low reliability, perfect for small, temporary setups. Star is your golden middle ground, medium cost, high reliability, dominating our homes and offices. If you need massive scalability for an enterprise, Tree is your medium high-cost solution. And finally, if you need the absolute highest fault tolerance for something like a data center, you pay the premium cost for a mesh setup.
Ultimately, network topology defines the literal shape of our communication. It dictates the physical wires and the logical rules that allow information to flow across the globe in milliseconds. So next time you plug in an Ethernet cable, set up a smart home device, or send a critical file at work, take a moment to appreciate the invisible architecture that makes it all possible. And ask yourself, if you were setting up a system where every piece of your digital life depended on it staying online, which architecture would you trust? Keep that in mind as you navigate the interconnected world around you.